Remember how at the very beginning of all of this, increasing, decreasing, relative mins, relative maxes, and in section 3.4, concavity even also, the very first thing that we're supposed to think about is domain, right? And with domain, I know, it's a piecewise. You're like, I don't know. Well, okay, pause. We could technically graph this guy. I mean, he is having a y-intercept at 1. Now, x needs to be less than or equal to -1, so I'm not putting a point there. But I know that the slope is down 2 over 1. That's going to be a closed circle. And I can kind of imagine what that connection would look like. And then this one's going to be a parabola, an upwards-facing parabola that's been shifted down 2. Is that right? There we go. With a hole. We actually could... Oh, no, sorry. Greater than -1. My bad. It's going to have a hole not there. It's going to have a hole plugging in -1. -1. Oh, actually. That's ironic. It comes here, but this is already filled in from the line. So actually, these connect. What does that mean? Well, first of all, just because all the x's less than or equal to -1 are included and all the x's greater than -1 are included, first of all, the domain is all real numbers because every x has a y. Every x has a y. No x's are illegal. But the second question that we have to ask ourselves, especially with piecewise, are there any discontinuities? Okay, domain, no problems because every x has a y, but are there any discontinuities? And so to do that, either looking at the graph or looking at the equations, do these match up? And the answer is yes. Plugging in -1, I get -2 plus 1 is -1. Plugging in -1, remember, continuous, I just need to have the limits from below and above agree. So the at and the below actually does agree with the above. Both of them say, yeah, -1. So therefore, discontinuities? None. None. So domain, all real numbers, discontinuities, none. That's different than the example in notes that we did where there was a discontinuity. So ironically, actually, from the original function, I'm not taking any numbers to my sign chart. But we still need to look at our derivative because we don't just put domain and domain problems and discontinuities in the sign chart. We also put critical numbers. So critical numbers, how do I derive a piecewise function? Ooh, we don't have this one ready. Okay, what if I was to say don't get tricked by the trig notation? Okay, what if I say 0 over 0? Keep going. Okay, fine. What if I say derive a piecewise? You guys say piece by piece. So derive a piecewise? What do I mean? Derive a piecewise? What do I mean? Piece, derive it. What do you get? 2 by piece. What do you get? No big deal. Piece by piece. Now here's the struggle. For a derivative to exist, a derivative, wait, definition of derivative, how does it start? F prime of x equals, oh, come on, before the power rule, before all the rules. F prime of x equals definition of derivative. The limit. Good. In order for a limit to exist, what has to be true? They have to agree. So, this guy's totally good for everything less than -1. This guy's totally good for everything greater than -1. But in order for a derivative to exist at -1, both sides must agree. The derivative, which is a limit, both sides must agree. So plug in. We already plugged in here and figured out they agree. No discontinuities. But plug in here. Plugging in -1, it's just 2 no matter what. Plugging in -1, ooh, what would that be? Does +2 and -2 match? No. So guess what's going on? F prime does not exist where? -1. We're not just looking for DNEs, we're also looking for critical numbers. Not just these guys. Who are those guys? Zeros. Set 2 equal to 0. Doesn't happen. Okay, fine. Set 2x equal to 0. Ooh, that'll happen if x equals 0. Is 0 allowed in this interval? Yeah. Okay, cool. So I also have f prime equals 0 at 0. So it's not quite like a pitchfork because you don't have a top and a bottom, but for a piecewise we say, hey, do they match up? If not, that's a DNE. Then we say equal to 0. Equal to 0. Yeah, 0 works. Equal to 0 at 0. Cool. So that's why, Patricia, we would put in -1. and 0 to our sign chart, we would go ahead and test the sign of f prime like we always do, trying to figure out the increasing, decreasing of f, or the behavior of f. When you plug in -2 for a piecewise, remember plugging into the derivative, sign of f prime. -2, you just have to check which interval before you plug in, but -2 fits here, that's a positive number. -0.5, fits here, that's a negative number. And then +1 or 2 or 5 or 10, whatever, fits here, and that's a positive number. And that's how we get our increasing, decreasing, increasing. And for relative extrema, we just have to ask ourselves the question, is there a change in sign of the derivative? Yes. And is the original function continuous there? Existing and continuous? Yeah, because there were no problems. So therefore I have a relative, you guys see it, right? A max where? Good. Sorry, -1. And then we have a relative min where? Good. Is that cool? Anything else on the evens, guys? Do you know? Or a question about that? Because, right here, right? Because derivatives are limits, like at their core, and limits in order to exist must agree from either side. So the problem is with our piece by piece, the separators derivative won't exist if these don't match up. So long story short, it's a sharp point. How do I know it's a sharp point without a graph? If I plug in -1 and say, what would the slope be as I come towards -1 from below? 2. What would the slope be as I come towards -1 from above? -2. Those slopes aren't agreeing. It's going to clash and be a sharp point. Does that kind of make sense? So the equation can kind of show me, as long as I test the below and above, that there's going to be a sharp point. And if there's a sharp point, the derivative doesn't exist. So I can't say the derivative equals or exists at -1. Yeah. That's the hard part about piece by piece, is you have to check the separator before putting the or equal to on either side. But you're right, if it would have worked, we would have just kept it like this. But since it didn't work, we had to take it away. All right, anything else from the evens of section 3.3? Okay, any derivative on 3.4 that we were like, Anything 3.4? Homework 20A, derivative simplified. Give me a page number just so I can be ready just in case. 245. Sorry, I didn't hear if someone asked. Ruth. 57, okay. Ooh, why is he nasty? Yeah, inverse secant. I mean arcsecant, but arcsecant is inverse secant, right? So before you find the, which derivative are you finding for section 3.4? But to find the second, you have to find the, so then we have to go ahead and find f prime first, which arcsecant is +1 over absolute value of u times the square root of u squared minus 1 times u prime is just 1, thank goodness, minus 1. Now, maybe some of you would have been like, I need a common denominator, but we're going a second derivative anyway. And what's the derivative of -1 going to be right here? Okay, well then don't worry about making it nice and pretty up here. Just go ahead and take the second derivative and be like, whew, he's gone. Right? So how do I take the derivative of that guy? How many of you guys are thinking in your head right now, quotient rule? Okay. How many of you guys are thinking making it all to the -1 power? Whew. Split, divided house. Let's do quotient rule. If I do bottom d top, what's the derivative of 1? Oh, sweet. There we go. Minus top d bottom. We can all agree that's not going to be fun. So we'll get back to that in a second. All over bottom okay. What do you guys see in the bottom? What rule do you need when you do d bottom? Product rule. So I can do second d. So this guy stays the same. Derivative of absolute value is the absolute value. No. We did it backwards, didn't we? Either way is fine. u over absolute value of u times u prime is just 1. That's fine. Plus first d second. How do I take the derivative of this guy? What should I be thinking? Yeah, make it to the 1/2 power. I agree, rewriting it. So we can bring down the 1/2, making it a negative 1/2 power, which remember puts that as a square root in the denominator. But don't forget your u prime. Good. Don't forget your u prime. So as we go ahead and simplify, I don't know, I guess I see that guy simplifying. I see like multiple absolute value of x things going on, and then I have like stuff down here. I see an x that we can pull out, but I also see this stuck denominator thing. Let me go ahead and maybe pull out some stuff that's in common. Like I see an x that's in common, so I could go ahead and pull out a negative x. Then I have square root of x squared minus 1 plus the x is gone, absolute value of x over, well, that's silly. They just change orders, don't they? They just change orders. Oh, wait. Oh, no, it's addition, not multiplication. That would have been really nice. Down here, I end up with that guy squared, and then a square root squared ends up just being himself, so x squared minus 1. I think I need to simplify this complex fraction. Don't you guys agree? So I'm going to multiply top and bottom by absolute value of x and x squared minus 1, because I need to go ahead and get rid of both of these guys. As I distribute to both, let's see what we have left. So that guy simplifies. I have this guy squared, which will just be himself, I suppose, huh? Square root squared. This one, square root, simplifies, and I have this guy. And then we have what we did on the top, we need on the bottom. That was horribly illegal. Lo siento. So then we have another absolute value of x times x squared minus 1. If you guys notice, we could go ahead and combine these two to b to the 3/2 power. So we could have absolute value of x cubed, and then we have x squared minus 1 to the 3/2 power, because it's 1.5 powers. Up top, I do have this little negative x guy who's chilling. Now here's the weird thing about absolute value squared. Doesn't absolute value just mean keep them positive? But what happens if you square him? He's going to be positive. Yeah, so actually that's redundant here, because the squared says he's positive anyway after you square him. So we could actually just make this x squared, take out the absolute value, and say if he's squared, it's a positive quantity. Squared plus x squared is 2x squared minus 1. We could actually be snazzy and just take out this x and make that a squared, because remember the absolute value once again is just keeping it positive. And then actually absolute value squared, that's going to be a positive anyway. We could actually just say, hey, those are redundant and make them parentheses. But the long story short is, if you're looking for zeros and DNEs, whether you x there, whether you simplify the guy that you have to deal with, whatever you did there, x equals to deal with, and you're also going to get x equals plus or minus square root of 1, and you're going to get x is equal to plus or minus. Wait, is that a minus 1? Yeah. So checking out all of our different special numbers, 0 plus or minus 1 plus or minus square root of 1/2. Even if you didn't know how to simplify very well. The one part that would have been positive, so we can go combine those two. That was the hard part, besides the derivative rule stuff. Okay, I'm going to go ahead and post by lunchtime the answers like I did for 19A for 20A, so you guys have the derivatives and the, wait a minute, what are these things called? They were called critical numbers when we had first derivatives. What are they called for second derivatives? Pips. Let's go talk about them, because we need to figure out how to use all this stuff that you guys worked so hard trying to get last night in homework 20A. We got one nasty derivative in, but let's go talk about what we're supposed to do with this stuff. Nice thing is, it's not that much beyond what we did in section 3.3. It really isn't. Because with all of your derivative work, you should have the second derivative, and here's the dealio. With your second derivative, sine of f double prime. With your second derivative, sine of f double prime. Instead of calling it C1 and C2, I'm going to call it P1 and P2 because it's not a critical number. It's technically a pip. Sine of f double prime. And then I can say increasing, decreasing f prime and concavity of f. There's a few different things that we can do. Let me try to make it a little bit more precise. Sine of f double prime, what it tells us about f prime and what it tells us about f. So our number line just got a little bit bigger or a little bit longer, a little bit more involved. Because now we're looking at the second derivative, and if the second derivative in between like a p, if the second derivative is positive, is that what we're talking about? Yeah, so concave up. If the second derivative is positive, what that means is box prime, f prime's prime, f prime is increasing because it's only one derivative away from f prime, but it's two derivatives away from f. So when you think about how removed a derivative is, in some senses, it's a way of remembering. If the second derivative is positive, or wherever the second derivative is positive, f prime is increasing, but f is concave up. And then if we had the second derivative being negative, and I guess we don't technically have to show, I'm just showing that pips are what we do with the second derivative sign chart. The second derivative is negative, then our f prime is decreasing because a derivative of a quantity, the first derivative's derivative, that sign shows us the increasing or decreasing. No. But it's 2 removed from f, so that's how we would know down. And if f double prime is 0, then f prime is constant. At that point, I don't like at that point, but we can. If f double prime is equal to 0, f prime is constant at that point, aka f prime isn't increasing or decreasing. And it's possible that f has a possible inflection point. Now over here, realize not just zeros though, also DNEs, just like we did with critical numbers, zeros and DNEs. Just now we're looking at the second derivative, not the first, which is why you guys had to do second derivatives. Check the original function for discontinuities, so check for domain problems, but also check, maybe we should just write this, the separators of piecewise, because that's what you guys noticed in homework that you need to do. Check the separators of piecewise to see if there's a discontinuity and just natural domain problems. And then down here, the sign chart is going to be with the second derivative. We're going to use discontinuities, any domain problems, any problems from number 1. You're going to use any pips from number 2. You're not using the pitchfork of the first derivative for concavity. You're using the pitchfork of the second. Making your number line or making your chart, whichever one you want to do. Still plugging in a test point, seeing the sign of the second derivative, and being able to sketch the conclusion of the original and or f prime. Because you can not only talk about f, you can also talk about f prime. You can talk about f's concavity and f prime's increasing, decreasing. Because as we saw yesterday, concavity is defined by the derivative or the tangent lines increasing, concave up, whichever branch you are, or by the slope tangent derivatives decreasing, whatever branch you are of a concave down graph. So with that, how do we figure out this guy's concavity? What do you guys think? Yeah, we got to take some derivatives. Now what's the nice thing? Wish all of homework was like that, right? Because for your first derivative, all you got to do is power rule. Could you simplify this right now? Yeah, but then you would need product rule. Why not just go take the second derivative now? And you would have 36x squared minus for x simplified, derivative simplified, right? Once I have my second derivative simplified, now what? Yeah, denominator. I don't need to set the bottom equal to 0, just set the top equal to 0. And we have, they're not called crits, they're called pips now. X equals 0 and x equals 3 halves. We didn't specifically do this, but I figured since it's a polynomial, you guys knew no domain problems, no jumps, no holes, no vertical asymptotes. Just going from negative infinity to infinity. So what we're going to do when we get to our line chart, let me make a chart. Let me make a chart. You guys know I like the number lines, but I'll make a chart this time. 4 lines. What? You don't necessarily have to do 4 rows every time. But let's see why I'm doing it this time. We're going to do our test after we do our intervals. Wait, intervals are easy. It's negative infinity to, where am I starting first? And that's 0. Oh, did I add that wrong? I did. Thanks, Ryan. I didn't think through the steps. I just put the 2 numbers together. That's a struggle. I'm acting like students. 2/3 to infinity. Test values. I don't know. What do you guys think? Negative 1? 1? No, 1/2. Aw. 1. That works, right? Then we're going to figure out our double. Increasing of f prime, and that can tell us about the concavity of f. You don't always need to know everything, but that's technically what the sign of the second derivative tells us. Where are we plugging this in again? Careful, if you plug it into the wrong space, you might have the signs be totally thrown off. And I wouldn't throw it into that one. That's gross. I would throw it into the factored one because we're just figuring out the sign. So for instance, a negative 1 times 12 is a negative number. And a negative 3 minus 2 is a negative number. A negative times a negative is a... Got to be careful of your mental math. Some of you messed that up in homework. Slow down a little bit if you need to. Show some scratch work if you need to. Plugging in a half, I have a positive number, but 3 halves minus 2 is a negative number. And plugging in 1, I have a positive times a positive. Which means my f prime, because once again, this is box, and f double prime is box prime, f prime's prime. F prime is increasing and then decreasing and then increasing, but what does that mean about the concavity? Concave up, concave down, and concave up. Now, what part of concave up? Well, we would actually have to go find the sign of f prime, like take our critical numbers from here. And we could actually come up here and we could say, let's take this guy, let's pull out a 12x squared. We'd end up with x minus 1. Our critical numbers are 0 and 1. Ugh, 0 and 1. We would have actually needed to split this up a little bit more to be able to figure that out. And we could have gone from 2/3 to 1, and then 1 to infinity if we wanted to do it that way. The hard part is, though, we would have like a couple intervals where we're just doing testing that we don't really need to for the second derivative, but we could figure out, let me show this a different way. We could kind of add on to this what's going on with our critical numbers, and we could do negative infinity to 0. We could do 0 to 2/3. We could do 2/3 to 1, and then we could do 1 to infinity. And we could kind of tack on a little sign of f prime. Figuring out the behavior, the increasing, decreasing of f. And if we were doing that, we would plug into the first derivative instead. So if we put these 2 sign charts together, if we wanted to know entirely what was going on, this tells us concavity, and that's true. I'm just making a point real quick. We would come back here and we would plug in. We would plug in negative 1, which would be a negative times a positive. We would plug in positive 1/2, which is a positive times a negative. We would plug in 4, a negative times a positive. And then we would plug in like 2. Oh, finally. What does that mean? If we put these two sign charts together, if f is decreasing and concave up, I could actually put those two together and say, oh, hey, so that means that f is technically doing this. Not just concave up, but this kind of concave up. And then if I know decreasing and concave down, I know not just concave down, it's actually going to be this kind of concave down. I could put decreasing with, this is still, oh, nope, it's concave up now. Decreasing concave up, this kind of concave up, and then increasing concave up, finally, this kind of concave up. So we could actually figure out exactly what's going on as far as taking the concavity and the increasing, decreasing. So I just want you guys to know, when I put the like one part of it, but the kind of concavity it's showing is up. The kind of showing is down. Is up. But you would need the increasing, decreasing to know exactly what part. And so that's why at the very end of this, because we're trying to get to, which will happen after break, taking all these clues that we're figuring out, all these behaviors that we're analyzing, oh, hey, does this make sense from what I just drew? It goes up, decreasing up, to decreasing down, to decreasing up, to increasing up. So we have this branch, and then a little bit of down, then a little bit of up, and then a lot more of up. So technically, all of those are exhibited in the graph. But we're trying to get to where we could get that graph, and so at that point, you are going to be doing increasing, decreasing sign charts and concavity sign charts. But this homework isn't putting it all together, not yet. This homework is specifically letting you focus on concavity. So let me bring this down. Let's get back to focusing on concavity. I just wanted you guys to realize when I write the little concave up, concave down, I don't mean the graph necessarily is a full cup or a full frown. Oh, where'd he go? I lost him. It could just be one piece of it, like you guys just saw. Can you see points of inflection? Is it there? Okay. Points of inflection. Actually, I can show you this on the graph that we just did. There's two points of inflection. One is right here. The other one is right here. There's one at 0, and there's one at 1/2. There are 2 points of inflection, and because a point of inflection is a point at which concavity changes. See, up before and down after, not for very long, but it goes down for a little bit. That's a point of inflection between the concavities. And then it's down for a little bit and then up. That's a point of inflection between the concavities. And how can I tell that? Sign chart. Second derivative sign changes, aka the concavity of the original change. So that's what's going on here. A point of inflection is a point at which, or we could say a pip at which f double prime changes. But that's exactly what we're going to say down here. A point at which concavity changes, specifically a pip at which f double prime changes signs. How can they occur? Well, they can occur if you have something like a concave up to concave down. That would be a pip. They can occur when you have something weird, like what we just saw. Not just where it's super obvious, but also where it's not so super obvious, from the down to the up. And then here's another one where concavity changes. Now, let me actually, this would be a DNE, this would be a critical number. What if I make it a critical number-ish? There's nothing special about that slope besides the fact that the slope changes from up to down. I should say from getting higher to getting lower. There's nothing special about that slope. This one could be a 0, that could be a critical number. This one could be a 0, that could be a critical number. That one, well, that one's just a negative slope. What's the big deal? It's not a critical number. Oh, we don't find points of inflection with critical numbers. We find them with pips. What's special isn't so much that it's flat, because this one's not flat, neither is that one. What's special isn't that it's flat or that it's vertical. What's special is that the slopes change from going lower to going higher, going more negative to going more positive. The slopes change behavior, not so much the actual tangent lines. The slopes change behavior, not so much the actual tangent lines. My, what's this? That's fun. Someone heard me complaining about how Christmas is coming too early. That's sweet. Okay, coming back. So what's going on here? Possible inflection points, who are these guys? Pips. How do I find them? F double prime pitchfork. But actual inflection points, it's a pip where the F double prime changes sign, aka the concavity of F changes, aka F prime changes from increasing to decreasing or decreasing to increasing. And I'm going to actually add that last part. Because remember, yesterday, what was the homework spiral problem that some of you guys got stuck on a little bit? Back of our homework spirals, what was that problem? What were they giving us? Yeah, the graph of F prime. Remember how it made it trickier for like relative extrema and critical numbers? Guess what they could do for points of inflection also? Give us a graph of F prime and try to trick us. But if we have a clue about F prime, well then maybe it won't be too bad. So F double prime sign changes, aka the concavity of F changes, aka F prime changes from increasing to decreasing. Sorry, all four. Not all four connected. This is, and if I were you, I would highlight possible versus actual. Actual ones truly is a sign change. This is, I know, there's a lot of them this chapter. There's a forever quiz after break. Over break, you're going to be studying those forevers. But forever number 24. We're almost to the end of our forever cards. We only have one more, and we'll see it tomorrow if we don't today. Oops, too much fun. Sorry. And then you just saw the function that you're supposed to be analyzing. Oh, well, that's okay. Okay. So guys, what's going on with this example? Oh no, this is what homework is tonight? Yeah, but what did you already do? Okay, you already found derivatives. So you guys start playing with that derivative. I'm going to play with it back here just to model the whole, like, hey, you have homework 20A. That you're going to be able to steal the derivatives from. You guys go ahead and play with it just a little bit. I will back here just to model the whole, oh, it's done on a separate page and we're using it. Remember the green trick. What am I talking about, green trick? If you don't use it now, it's going to be awful. What's the green trick? Look for what's in common. Yeah? Bottom d top minus top d bottom. Don't forget u squared. The derivative is 2u times u prime. What's the struggle? You're going to feel so accomplished when you get the first derivative, and what do you still need to do? Right? bottom, d top, minus top, d bottom. Derivative of u cubed is 3u squared times u prime. Bless you. 3 squared, 3, 6. There we go. Please use the green trick. Did you guys have ones like this in homework last night for 20A? Not too bad. Well, you can pull out a negative 3 from this guy. That'd be negative 3x minus 3. We'll pull out a negative 3. When you pull out 2 of those guys, 4 of them left down there. Maybe you have 1 left. Pulled out the negative, so I have a plus. The 3's gone, the negative's gone, those 2 are gone. Do you guys see how it's a bit of a beast? But why am I going to all the work of simplifying? What do I need to do to this guy? I need to pitchfork. And to pitchfork, I need it all nice and factored and simplified, right? So then I end up with, did anybody get my first derivative to match? Or your first derivative to match? Uh-oh. Patricia says yes, Rachel says no. Rachel. I would have pulled out the, would have had this left. Oh my. Thank you. Rachel, this is for you. You guys. You guys. What do we have to do? Do we have to multiply this guy by that guy and get a cubic polynomial and factor? I think so. But what's the end game? The end game is to pitchfork, just because we're running out of time. The end game is to pitchfork. And with those, what do we call the zeros and DNEs of the second derivative? Pips. What do we do with those pips? Like a chart. But what do we get to do in homework now that you've worked so hard on homework 20A? We're going to come over here and say, hey, guess what? F double prime equals. Yay! And you have the answer key on. So you can go make sure you're, please do not go doing sign charts before you've checked your derivatives for the evens and the odds. You can go steal the simplified derivative, then you can go ahead and take your pips, but don't forget, way back here. Also the domain. Set this guy and tried to figure out if he has any factors. And if you're like, wait, but the x method doesn't work, couldn't you always do x equals negative b? Plus or minus square root b squared minus 4 ac. Is it bad if I have 1 minus 4 under a square root when I'm looking for zeros? Isn't that imaginary? Guess what? He doesn't have any whole denominator. The domain is all real numbers, even though there's a actually. Those pips, we're going to go ahead and make a chart where we think about the sign of f double prime to figure out what's going on with f prime, but really what's going on with f as to whether it's concave up or concave down, because this guy is increasing, decreasing. So guys, in your sign charts tonight, when you're testing, if you technically need this step, what you technically need is just the sign of the second derivative going to the concavity of f using your nice and pretty simplified critical numbers. Now, keep your eye open, because there was one more forever card. There's one forever card we didn't get to today. So I'm going to go ahead and adjust the assignment as far as what it is due. I'm posting. Ignore from here on because we need to go finish that in class tomorrow. But fully attempt everything up to then. Bye, guys. Ugh, I need to finish. Oh, how did I forget that? Yeah.